Welcome to this College Algebra training video. In the BYU-Idaho College Algebra classes, they do labs. In the labs, they use discovery learning to find out about functions. As your assignment today, you will do a lab about ramen noodles and exponential cooling. In this video, we're going to do something similar. The numbers will be different, but the questions will be very much the same. So some College Algebra students will do this lab in class, and others will need your help with it as they do it outside of class time. You also want to prepare to just help College Algebra students think outside the box, because they may have never done a lab in a math class before. Let's look at some ramen. This is a lab about different ideas behind how things cool down. We'll use ramen as the food that is cooling down. So remember, these numbers will be different than on your assignment, but the questions will be very similar. First, we're going to assume that the temperature of the ramen goes down by the same number of degrees each minute. So right after the microwave at 0 minutes, it's 100 degrees, it's at boiling. That's 100 degrees Celsius. And we're going to fill in the table for how much it's going down each time. So after 1 minute, it's 94 degrees, which means it has gone down 6 minutes. Okay, so at 2 more minutes, it'd be at 88 degrees, or it's gone down 6 again. And at 3 minutes, it's gone down 82. Notice the table is not at 4 the next minute, right? So we're going to skip to 5, then we're going to skip to 18. So we really need to think about how to find the temperature other than just subtracting 6 lots and lots of times. This is a constant rate, though. Every time it does go down by 6. So if we start at 100, go down by 6 every time, we could just multiply that by the time. Let's use t for time instead of x. T for time. Okay, so at 5 minutes, we can plug in 100 minus 6 times 5, right? That's 30, so we'll subtract off 30, and we have 70. And then we can do the same thing for 18, 100 minus 6 times 18, just to jump ahead. That would give us negative 8. 6 times 18 is 108. All right, so it's gone down 6 degrees. It's already negative 8 degrees after only 18 minutes there. But let's think about this in a different way. Let's say instead of just dropping 6 degrees, it's dropping by a certain percentage. This is our second assumption, our second law of cooling. Okay, so we start out with the same first two measurements, 100 and 94, but in this one it says it's going down by a percentage. So it's going down by 6% every time. Not 6 degrees, 6%. And so instead of subtracting 6, we need to figure out what 6% of 94 is, and then take that off. Or we could just multiply by 94%, because that's how much of the temperature of the heat is left after we take off 6%. So our next step would be to take 0.094, whoops, decimal's in the wrong spot, 0.094, and multiply that by 94. Just like here, to get 94, we would have multiplied 0.94 times 100 to get that step. So this ends up being 88.36. Okay, and then we're going to take that reference point, 88.36, and multiply that by 94% for our next one. That ends up being 83.058. We'll round to that number. Notice right now, if we compare the two tables, they are not very different. 100, 94, 88, 88.36, 82, 83, so they are pretty close together. But that's about to change once we get to 18. But let's think about, because remember the next one is not 4, and so I can't just multiply by 0.94 times 83. But let's see what the pattern is on this one, right? So if we start at 100, the first thing we did was multiply by 0.94. And then for the next minute, we did that again. And for the next minute, we did that again. Every time we are repeatedly multiplying by 94%. And so what we can do is we can just say we're going to do that the t number of times, right? So at 0, minutes, that would become 1, and multiply by 100, we're at 100 degrees. If we plug in 1 for 1 minute, then we'd be at 94 degrees. And so we're going to plug that in for number 5 here. So that's 100 times 0.94. And we're going to say t is equal to 5. That multiplies in the calculator to 73.39, which we would do if we did 4 first and then 5. We'd get there eventually. So let's go ahead and plug that in for 18. So you're going to do 0.94 to the 18th power and then multiply that by 100. You get 32.8, which is, whoa, that's not an 8. 832, which is very different than what we saw at 18 minutes with the other law of cooling. Right, so here we have a constant rate, so this is a linear, and this is a exponential model. Actually, exponential decay because it's going down. Oh, I'm running out of room. Exponential decay. It's going down. So what I want you to do right now, before we go on, is I want you to pause the video and think about which of these you think is more accurate to the situation of ramen cooling down, and don't push play until you have one that you picked. Okay, welcome back. Hopefully you've picked something. I feel a little bit like Dora the Explorer sometimes when I'm like, pause and think about it. Did you really? No, I think you've made a good choice. Hopefully, what I think, which is more accurate to this situation, is that exponential decay is more accurate, because a linear model would just keep going down even past like freezing and negative, and so it would never level off, which I think the temperature will level off of this ramen. We're going to talk about that next. So the exponential decay model is more accurate for our situation of cooling off the ramen. But, however, does it make sense for it to go all the way to 0? Think about this. Okay, so here's our equation. We said function of time, 100 times 0.94, that's our 94%, and our variable right there, t, is the minutes. Let's say your apartment is at 25 degrees Celsius. If you have the ramen just sitting on the counter, is it going to go below 25? Because remember, we saw on the table, it was already at 32 at 18. So eventually it would go below that. Think about if you left it in your apartment for 6 hours and you just forgot to eat. That happens to college students sometimes, right? Let's calculate this. Let's try it with the equation. So we'd have f of 6 hours, so that's 360 minutes. We plug that in. So that'd be 100 times 0.94. And our t is 360. That actually, in the calculator, gives you a number in scientific notation. So it's really, really small. Times 10 to the negative 8. So almost 0. Right? So it would level off maybe at 0. Not maybe, sorry. It would level off at 0. This function actually has a horizontal asymptote at 0. When you look at functions, exponential functions, let's just write this a to b, well, you can keep it x. We'll just use our standard form here, x minus h plus k. You've seen that before. The k, the thing being added to the y, is the horizontal asymptote. And so here we have plus 0, that means the horizontal asymptote is 0. It's going to level us off at 0. If your apartment is at 25, that's not going to work. Doesn't make sense. So what I want you to think about is how you can make an equation that considers that limit of the apartment temperature, 25. Pause the video and see what ideas you come up with. Okay, hopefully you got some good ideas. Let's go back to this idea of horizontal asymptote. So we know that we want it to level out at room temperature. So if we use this basic equation again, we know that we want it to be plus 25. 25, we want it to be our horizontal asymptote. And we already know b is 0.94, and we're just going to keep our variable of t, time, plus 25. So what we have to figure out is what A would be, if it's going to stay 100 or not, right? We do, however, know at least the first data points, right? We know that when you take it out of the microwave, it is at 100. And the time would be 0. So what we can use is we can use that data set because we don't want it to change. We know that when you take it out of the microwave, it's going to be 100. That's already in our assumptions. And so we can't change that to be 125. Right? So let's go ahead and solve this. 0.94 to the 0 power, oh, I love that, is 1. A plus 25 equals 100. Come over here. So we can solve them by subtracting 25 and we get 75 equals A. So our equation would be y equal, let's go back to f of t, right? Function of time. A is 75, B is 0.94, t is our variable, and plus 25. Let me go ahead and show you the graph of that. Make some room because the graph's going to go right here. Okay, close enough. Alright, so on this graph, we have 0 and 100 like we wanted, and we also have a limit of 25, and it is still an exponential decay with the ratio of 94% each time. So that'll work. We just have to adjust it for the temperature of the room. Alright, one more question to look at, and then you will be set to do your assignment to help out with the labs. So let's say you want the ramen to be 50 degrees Celsius when you eat it. We want to figure out how long you should wait. So that 50 degrees is going to be our y, or our f of t. We're going to plug that in. Okay, hopefully you've done lots of solving with exponential equations. I know there's another video about that that you'll watch this week. But let's go ahead and solve for t when it's not a variable exponent right there. Subtract 25. 25 equals 75 times 0.94. Divide both sides by 75. Just so far, just normal equation procedure. We get 1/3, 0.94 t. All right, let's go ahead and solve this. This is the tricky part. Involves exponents and logarithms. So whenever you have a variable in the exponent, you want to use logarithms to get them out. And whichever logarithm we want to use, I love using the natural log. So I'm going to do that to both sides. As long as you do it to both sides, you're keeping the balance. And we have that rule that says the variable, or the exponent, can come down in front of the logarithm. So we'll do that. And we have just the constant times t, so we'll divide it. And we'll set subtract and then divide. Plug that all in your calculator and you get t equals 17 point, I'm gonna round that to 76. So after about 17, almost 18 minutes, then your ramen will be ready to eat. You can wait that long. I don't think I can wait that long for ramen. But it'll be 50 degrees at that time. Alright, you are ready to help out with some labs. Math 110 especially, make sure you're helping them to think outside of the box with these. Well done.